Okay, here we go. Week 12 for PLC 3. We're going to be talking about the safety PLC this week. And you're accessing this because you probably clicked this video here or else you're subscribed to the channel. My students are doing that. But here we go. I got phase quiz here, so we took that. Hopefully you did that. And we're finally getting all caught up on servo drives. I said don't worry too much about that. We will get the servo drive lab done this week, and then we'll start transitioning into the safety PLC. And then we'll actually apply the safety PLC to the servo drive. So I can take that safety PLC to servo. That's what we'll eventually be bleeding into here. I got some new handouts, guide sheet, homeworks lab. There's a lot of D2L reading. I could really put a lot of D2L reading up there on this, but we'll figure out what everybody needs here as we go. And then there's a light curtain control board. I'm bringing one in. We'll build up a couple of these for you to use, but you'll get a little, you can help me out by getting these wired up, all right? But before we get into it, we're going to talk about our servo motor, where our review from last week where we did stepper and servos. We did a stepper motor just for fun. It actually was kind of fun. There's a lot of people in the department talking about how fun that was using a relay card to move that like we wanted to. We did the servo motor, and then we did the HMI control of the servo motor using the state machine. So that was good that we went through the state machine lab so that you could see the way that servo motor worked. But with the stepper motor, we used a relay card to simulate the stepper motor control. So like I said, this is kind of almost like a legendary lab already, just because the relay card was clicking pretty fast. We set the interval pretty short, maybe like 10 on that SLC 500 until 0.01 timer. So even moving pretty darn fast, those relays did. That motor, you know, that screw drive didn't move very fast, right? So that just gives you an idea why I want to do it, about the solid state nature of how that stepper motor controller would manage the speed and the current requirements to drive that motor. It would be very fast, and it'd have to pop through that, you know, if you had significantly higher current, it'd have to manage all that. And you could really get those, stepper motors to really move if you wanted to. So hopefully just that just for fun, you know, you get the idea of it. Plus we got to use the SLC 500 again, and it was kind of a good review of how to use some of that stuff. We use the SQO command, and it's a little bit different than Logix. Remember, Logix, when you start using, you know, creating all this data here, it's just user defined. It doesn't have a spot in the memory allocation of the controller. It's when you come up with a tag, at that point it's created, whereas R6, binaries, integers, whatever, there's already space set aside for this. And you have, you know, some limitations of how much data you could actually store here. But yeah, we did pretty good coming through and remembering or applying what we've learned with the control logics in backwards to the SLC 500, and it went pretty well. Had to do, maybe some of you did a little YouTube to figure it out, but it was good. The energized state, just it was interesting to note, hopefully everybody did this, that when the stepper and servo motors were energized or had, you know, the right voltage to them, it was hard to manually rotate that shaft or that screw drive. And the stepper motor is just powered on. And remember that stepper motor, what's nice about that is it was a 5 VDC supply. And you know, I didn't want to burn up that relay card. And we weren't going to have that problem because I don't think there was going to be a lot of current here, but hey, you never know. The servo motor is when the MSO instruction is on, and boom, all of a sudden that shaft gets locked. That shaft gets locked on. Okay. Halfers full step. We full step that stepper motor. We use a 200 preset counter and verify that, yeah, that shaft did turn 360 degrees. It was right on. You ran it multiple times, one turn, you know, a full revolution, a full revolution, a full revolution. So you could tell that you can use that stepper motor to control the rotation, and you can get to an exact location. The half step would require 400 steps, a step signal and a direction signal a little bit different. And then what we did is we measured the linear travel of that screw drive of about 5 millimeters per turn, And that's pretty critical, because whatever you are going to mate this to, some type of linear travel device, the screwdriver was pretty cool. It worked great. But you're going to have to configure that, and be sure that your rotations, the speed and number of rotations, is equating to some outcome. And you can do this within the software, for example, with the servo motor, but not all applications are like that. But we'll have to be setting that up, where we set that up for the servo motors, that we had to put in the pitch basically in there so it would work. We did the 5500 servo, Kinetics 5500 servo, and you build up a trainer, which is good for yourself and for future classes, just to see some of the different connections on there. Ours was 230 VAC. Oh my, what did we do here? Yeah. And I had a single phase step up to bring the voltage into there. If you remember, so ours was a single phase 230, and it made three phase, very similar to our PowerFlex VFDs. They were single phase in and made three phase 230, but I used a little transformer on there. But really, you can just get three phase 480, three phase 480 power flexes and connects and stuff like that. You're going to see a lot of that, because that's what the voltage is. But our little ones work, and you got to make some connections to get the right voltage. 24 VDC. We had some digital inputs and digital outputs, so depending on the type of proximity switch I gave you, got to hook that up, 2-wire or 3-wire DC. You had to do your motor cables, your power, and your encoder cables, and then you had your safety contacts. And so we'll get into that, the DCS safety contacts this week, because you want to add in your safety PLC to control the kinetics. And how far we get with that, it's up to you. There's a lot of safe torque off and all this kind of stuff that you can do with the servo motor. I can write that here, safe torque off. That's a little bit different, or we can just bring it down completely. But we can take a look at that this week. The programming, the program I gave you operated using the state manager. You basically energize the servo. You have to clear, the fault's supposed to be cleared. You have to have a clean state there, or it's not going to go. But that was what the code did. It energized it, cleared the slate, and then moved to precise positions. You could indicate the speed you threw in. We were throwing in travel in millimeters, I think, and we just get it to move back and forth a little bit. And you could see that how you could set the A cell and the D cell. We took a look at some created a trend just to see how linear it was, or was it slowing down with it, some acceleration or deceleration. So the trend was interesting, just to see how it was moving, right? And then we did the HMI control, and once again we can use the HMI to control and monitor to the position, or just control the servo motor to move. Our position was monitored by the rotary encoder on the motor, because that's how this servo motor is working. It's got a rotary encoder on that. We'll go through it again just a little bit. We did that last time. But a linear encoder is often added to a system to verify positioning as well. So throw in a linear scaler, a voltage divider. A voltage divider is what I have in the classroom for you to take a look at. And you could certainly put this a linear encoder on the screw drive, and then if you set the pitch right and you say, hey, move 200 millimeters, you could verify that with an analog input card that, yeah, this is moving like what we wanted it to. Now, on the stepper motor, because the stepper motor is not a feedback loop, it's not closed, you could put this voltage divider, or this linear encoder, whatever technology you want for the linear encoder there, onto that stepper motor, and then you could definitely verify that it moved 200 millimeters or whatever, in case you're getting some slip or something like that. And that's that concept of closed loop that we were talking about. A servo motor uses positional feedback. It says either linear or rotary position, but typically we're thinking that servo motor is a rotary encoder, right? throw both on. Do a rotary and a linear if you want. If it's really critical that you know that you're where you're at, or if it's just I want to know if I'm there or not, put a proximity switch at the end, and that's what we did with our homing. We just put a prox with our homing so that we knew that where we were starting, right? But basically, yeah, that encoder just gives you the feedback, and then the controller compares the measured position to desired position, generates kind of an error signal, tries to keep itself moving in the right direction for the right amount of time at the right amount of speed. And that's our closed loop on our servo. Could make a quote closed loop stepper if we use that linear feedback, that voltage divider I gave you, but it's a concept of closed loop. We talked. These are just a few slides from a couple weeks ago when we were doing this. But remember, the type of encoders are either absolute or incremental. Simple servo motors use just resistive potentiometers as their position encoder. The incremental ones like this require homing, and that's what we did with ours. We put that inductive prox on there, and so when it backed up, first thing it did was it backed up, and we set the speed for that. We set the speed for the backup, so it just didn't take off at full speed until it hit the home. It basically moved slowly until it hit the home. And if for some reason you stopped the mechanism all the way down the screw drive and you homed it, well, it took a long time to home back because we were moving pretty slow when we were homing. But if you stopped it at the drive end, then when you hit homing, it only had to back up a few millimeters before it homed, right? The optical encoders, we're not going to go in and talk about how resolvers work and everything like that. You can go ahead and look up resolvers if you wanted to get into exactly how it works. But I think you probably get the idea of this. But the optical encoders are a fan favorite here, where you've just got the slits here and you pass light through there, and they can move very fast. You can count the breaks in the light, almost like a light curtain, and it can move very fast and do a fast count. And that optical encoder will keep track of where you're at. Mechanical system. And so, just to reiterate, we hooked ours to that screw drive. It worked out pretty good. A few little issues with that when I made those. I'm not going to tell you. Never mind. But I was in a hurry. Let's just put it that way. But they worked pretty good. And we set our homing to make. I think once again it was about 20 millimeters off of the hard stop. So you do not want to home probably directly into the hard stop. Put a little space there, maybe to home it just off of the hard stop. You can set soft stops in the software so that you can just like with a FANUC robot or something like that. You can set axis limits. Is what it is. So we only have one axis here, and you could set a soft stop so that if we have a 300 millimeter, we have 200 and 300 millimeter screw drives. So you could set the axis limit at 250 millimeters, for example, if you had the 300 millimeter, and that way it wouldn't get anywhere near close to hitting the hard stop. You want to try not to crash the drive into the hard stop. These motors are pretty tough, but I usually try and avoid any kind of running into the work cell with moving equipment if possible. Okay, but you could use homing. You have hard stops, worst case, and we have the proximity to set that, but you can also set your soft stops. And this was our little trainer. Once again, it moved back and forth. The only thing that we didn't have is the linear scale. I've got the linear scales there if you wanted to put one on and then wire it into the analog input card. It's the analog input is not built into the kinetic to the 5500. That would be nice if it was somehow, but it wasn't for the linear feedback. But that that would take a little separate operation, and then you can start looking at the error comparison instructions that we've been familiar with, like PID and this kind of stuff, and then you could get your system really dialed in here for maximum performance if you needed to. But remember, realistically, a lot of times the rotary encoder by itself is usually sufficient to get this to where it wants. Throw in a linear encoder if you want to double down on it, right? But what we're doing this week is, that was the review. What we're doing this week is the safety PLC. And we've been using these 5581 ES controllers this time. And remember, they're flashed to like version 37 or something like that. I see the latest version. They got some newer versions out. We might want to take a look at that. But the safety PLC is just a specialized controller that's designed to operate in a fail-safe manner. And we've talked quite a bit about safety. You guys do really well with a lot of the safety stuff that we've talked about so far. And you can just dig into this. You can dig into this forever to talk about, what is safe and how to do it. But they have built-in integrated safety functions. These redundancy, we've certainly learned a lot about redundancy in these safety systems and your diagnostics to meet international standards. Like here's one, IEC 61508. Well, what does that mean? 61508. Woo! We can go to town on this if we wanted to. And if that's your job someday, you might, learn all there is to learn about this. But it's out there, and there's certainly more of it than less of it, right? But what they do is they continuously monitor your safety inputs, safety devices, emergency stops, light curtains, hazards, and there's special logic that's used to shut down the machinery using the safety PLC. So once again, I just talked about the IEC 61508. It's an international standard that, one of the big things it does, it talks about the safety integrity level SIL. We already did this in week 2. So you might have to, if you want to back up and take a look at the week 2 stuff, the PowerPoint, or at least you don't need to listen to the lecture, but if you just want to go through the slides of week 2 where we broke down, some of these basic concepts, go for it. It's all foundational or fundamental. And as I'll say it again, that we're not going to become experts in this class about this. We're just introducing, how this works and why you would want some of this stuff. But some of the factors from this is that, once again, this is just a review from week 2, is we talked about, what safety, freedom of unacceptable risk. And you're like, well, there's an acceptable risk and an unacceptable risk. Absolutely. And a lot of it's based on physical injury, which would be the highest factor. But you also don't want to destroy your work cell by having things run into each other or blow up or catch on fire or anything like that might be related to the safety. And the risk is a combination of the probability. You're trying to figure out, would a hazardous event occur? And if it did, what would be the severity of the damage? So if it's hazardous but there's no damage, what does that mean? Is it really hazardous then? But there's a combination and probability of this. Your functional safety is the safety system performing correctly, and then you obviously have a life cycle. It's got to be repeatable for a time. So SIL, we talked about this. It's a quantitative measure to specify the required risk. There are 4 SIL levels, 1 through 4, 4 being the highest. And Alan Bradley did some analysis a few years back to see what people were doing with their equipment. And really very few applications were using the highest level, maybe like 15%. Most applications were like at SIL level 2, maybe be a little bit higher here. And then, there's a few at SIL level 3, but SIL2 was where most of the applications were. So if you were designing a system and it was SIL2, well, then you're figuring out, are you using hardwired components? Are you using programmed components? And there's a function, there's a difference we'll go over between performance level and then the safety rated equipment to get you to that performance level. And that's what this SIL is related to. What kind of equipment are we using here? Okay. A couple of other common terms is your equipment under control. And this is your main system. So what we're doing here is we'll be doing dual safety contactors, again, supposedly turning on electric motor. You can bring the motor out, or bring the motor out, and we can turn on an electric motor. That's what we're going to be bringing our machinery. But we can also drive the Power Flex that we have, the 525s or the Kinetics 5500s here as well. This is some of the type of equipment that we would use. The control system, this is what the unit that monitors and directs the EUC. So what we're going to be doing this time is adding Ethernet safety I/O, and it's going to go on to our remote Ethernet IP training boards. We have to modify them a little bit because the safety inputs and the safety outputs are, they're double wide because they're DCS dual channel, and so we're going to have to add a few more connection points for these. We will take a look at that, but that's what we're doing. Our safety related system, and that's where we're going to be using those 5581 ES, those controllers, safety controllers. And then any kind of external risk reduction, there's other systems that can do this. Like, I don't know, you want to use a safety relay, master control relay for hardwired safety. Like, you can just keep putting on additional safety on top of safety on top of safety to be sure that you're getting the functional safety level that you need, that you predetermined, right? And it's sometimes a big activity to figure out what this is. I don't know that you'll ever do this in your life, or you'll be given the safety level and the equipment and stuff that you need, whether you're determining it or not. So that's what we were talking about, doing the hazard and risk analysis. And you'll do a safety assessment by identifying the hazards and stuff like this. Is that your job? I don't know. It may or it may not be someday, depending on what if you're a control engineer, or you just the PLC technician, or you higher level or lower level. But there's going to be some working safety analysis that somebody is doing somewhere, right? Your safety related functions. That is, what equipment are you gonna do? You got to monitor response safety related systems to monitor all the pressure, temperatures, and reduce harm. So all this equipment and all these, they're gonna have all these standards and everything to explain how this works. And whether you're doing it or not, we're doing it as an overview so that you know where this is coming from. All right. So it's coming from a lot of safety standards out there. So we just talked about 61508, and this is it's an A-level standard, and it's just kind of a lower level standards. There's A, B, and C's, and it's just really an overview of some safety. And what an A-level is going to reference more specific standards. So you'll get in here and you'll start learning about what this is, and you might have to go and do some more digging in some other standards. And the same with the B11 ANSI standards, kind of another A-level standard that is going to lead you to some more specific standards. And then you have and some other ones are ANSI RIA 1506. 15.06 is a great standard. It's been around a long time, and because it was robots and robots were dangerous. This standard came out a long time ago when there was really a lot of robots just being implemented. It's more specific to robot, and this RIA 15.06 really drove a lot of some of these safety standards as they relate to automated machine control systems. So that's a good one right there. Here's another one, ISO 13849. This is a good standard that you might get into if you're in machine control, systems, and that's what we've been studying a lot in this track. You're on the automation and control pathway. So this might be a good one that governs a lot, of what you're doing. Once again, here's some international safety standards, and some of them are for machinery, your control systems. And here's your PL rating, here's your SIL rating, machine guarding. There's just going to be a variety of different ones here, right? Two of the things that we studied related to these in week 2 was your performance level, and this is just a slide from there when we talked about performance level and your safety integrity level, SIL, and they're related, and it goes back to different standards. So remember, we had our safety performance level where we went through and talked about, well, what does this mean? Basic alarms, all the way up to, very high risk where you have presses, cranes, and stuff like that, where you can seriously get hurt. Okay, so safety performance level or SIL are some of the ones that you're gonna hear. Now we'll be doing some e-stops. So if you need to go back to week 2 and review your e-stop categories, there's that Allen Bradley safety handout and talks about your categories 0, 1, and 2 e-stops, and it talks about immediate stop, or do you de-energize everything, or stuff stays energized, or whatever. And you can go to the PowerPoint and take a look at a controlled stop versus immediate removal of power and all this kind of stuff, because we will be doing e-stop. And when you incorporate, a dual contactor, or are you talking about doing using it with the PowerFlex or the kinetics? All right. This is a review from week 2 where we were talking about scenario with the e-stop. If you remember that you start and then you take a look first. How severe is this? Are you maybe you're going to get a cut, which is not good. You don't want to get cut. Or are you going to is it very severe, an irreversible injury, like you're going to lose a finger or something like that? Well, then you start heading down each path, and then how frequent is it? Does it happen a lot? And is it possible to avoid that? And then so based on the way that we did this, we ended up with our low risk or high risk, and this was our performance level. And our performance level then set what we needed for protection. What kind of equipment we needed, what the system was going to look like, what kind of monitoring and everything like that. And then I'll say it again. I've already said it 5 times this presentation. I don't know that will be your job to figure this out, or maybe it is your job to figure this out, depending on where you're at with your job. But we're just trying to let you know that this is where it's coming from. And this is the other slide, performance level versus SIL. In general, SIL is the safety rating of your components. So, you need certain SIL rated components, and PL is your safety rating as a whole system that either you or somebody else figured out, right? And once you get that all figured out, there's going to be different types of machine safety devices that we've talked about. All these, certainly we've done a lot of dual channel emergency stops. This time we're going to add the curtains. We use relay safety contactors quite a bit. We're going to do a 2-hand control system again this time, and then your lockout tag system. So those are some of your safety devices, but we will be adding a new safety device we call a safety PLC, and that would be your guard logic processors. All right, so up to now we've just been kind of doing everything hardwired. What we have is the guard logic processors, but they can give you SIL2 or SIL3 safety depending on how you set them up. Okay. Or PLE. They can do SIL3, PLE, guard logic processors to build these safety systems. And that's going back to here, where we went to PL versus SIL, and we looked at some of the different items that are going to be determined over here, whether you're at PLE or not. Okay. But the guard logics can get used to SIL3, and that would be your L7 or L8 safety controllers, which is what we have. But you would need a safety partner on those because everything needs to be redundant. We don't have that. We have L8 controller, and we don't have a safety partner. So we're going to talk about a little bit about SIL2 is what we're going to mess around with, SIL2. And as I told you, they did a survey, and that's what quite a bit of the applications in this world were, was SIL2. So it works out good. The L81 features are 4 core systems: logic, communications, overhead, and safety. So they're pretty complicated. We talked about various asynchronous scans going on within inside of these, and so that's what's going on here. These have a safety signature for each application, and we're not gonna dig into that very much. But basically, when you create a safe application, a safe program, then you want to put a signature on it so so it's committed to that process. I guess maybe that's the way that you want to think about that. And then when you have the safety signature, if you want to change it, you have to get in there and kind of take that safety signature off and then create a new one because you want to lock that safety in. There's a video right here where it says safety signature. If you just want to watch the premise about how the safety signature works, I suggest you watch it. It's like 7 minutes. It's pretty cool. So you cannot force safety I/O off and on. We talked a lot about forcing, so yeah, that sounds like a good idea. It uses the black channel principle for safety network. So it is, we'll talk just briefly about it. It is transmitting over an unreliable network. You know, Ethernet's not reliable. You think it's reliable, but it's not. So we need to do something different for the safety network. You have a SNN safety network number. It's a unique identifier, once again, for your safety network so that you can apply your safety signature. There's the video right there. I suggest you watch it. Safety tag mapping. So we do want to still use some of our standard controller tags, some of our non-safety I/O, like let's say you have a normal push button or something to operate your stuff. Well, you have to create a safety tag map so that you can push that data and transfer that data back and forth between the safety routine and the normal routine. So standard logic can communicate with the safety routine. So there's a little 1.5 minute example here on safety tag mapping. When you get to the lab, you're going to have to watch that safety tag mapping. Not a big deal. The black channel concept, and we've already talked about redundant networks like ControlNet and stuff like that. It is a concept that allows safety critical data to be transmitted over an unreliable channel, okay? And the way you do that is you add a safety layer on top of the standard data. Well, boy, that sounds familiar. Once again, this dual channel safety, and inside of that is your error detection and your correction mechanisms, okay? So you have your underlying network, which is a standard non-safety rated network, such as Ethernet. But then you have a safety layer. It's implemented at the application level, tunneling safety data through the existing network, and it would have error checking. And it's just, once again, we're going back to your Ethernet connections in your redundancy. And redundancy, as I said, goes all the way back to ControlNet which was not safety rated necessarily, but you just wanted to be sure that your data was getting down the network like you wanted it to. As compared to like DeviceNet is not redundant like any of these. But when you're doing safety, you're definitely going to need some redundancy here because the data needs to get there safely. Okay, so we got off track a little bit there talking about the safety PLCs, but you know, up to now we've used a lot of safety relays. Okay, and what the idea is that a safety PLC can replace the functionality provided by safety relays, for example. It can do more than this, but we're just going to take a look at this. And we learned a long time ago in PLC 1 and about the second week that, you know, PLCs were originally designed to replace relays, or the vast majority of relays, to do logic, right? So sounds like safety PLCs are kind of an adaptation of that concept, but they would work to replace relays, but they would also work to replace safety relays, okay? And that's not all that safety PLCs can do, but that's what we're going to start with here, is getting rid of, you know, that redundancy that we'd learned how to incorporate, you know, with safety relays. When you're talking about a safety PLC versus relays, I got a little, you know, pros and cons here. Safety PLC obviously going to be much more complex, a lot of safety I/O, like currency stops, safety doors, whatever. Whereas the safety relay is still good for simple applications. We've done doors, we've done door switches, and we've done e-stops, and really the safety relay will work great for that. If you have a simple system and you can monitor and everything like that, we've done well with that. That concept is still valid, but if we can get rid of safety relays and just do it with a PLC, you know, you can do it. All right, it's more flexible. If you make changes to this, it's hardwired. So safety relay, you'd have to start wire cutting and wiring. Safety PLCs, you don't. Obviously, the more hardwired we get away from, the more we can just do diagnostics and monitoring with a computer. The safety PLC is going to have a high initial cost. but it might be, maybe it's long run, it would be better due to reduced wiring and troubleshooting and maintenance. Okay, so these are some of the pros and cons of this. And so, as I stated, we're going to start by, you know, we're going to apply a lot of the things that we've done using safety relays. We're just going to do it with safety PLC. Now the thing here is, Allen Bradley has different safety situations. Like, you know, every situation is going to be different. But what they've done, Allen Bradley has done a great job of publishing application manuals for specific hardware, software safety situations. And the beauty of it is it includes, and they kind of guarantee their safety analysis of this. So if you need a certain SIL level, you're trying to accomplish something, you can just go to this AB safety manual and do it. It's like you want to say, oh, I need a kinetics drive with, I want to control it with a guard logic, and I want, you know, this functionality with my light curtain or my door stop. Boom, it's there. You can go and search it and you can find it, or whatever safety thing that you want that you can think of. Go out there and you'll get something that's pretty close. And the beauty of it is it lists all the hardware that you need or would be using. It shows all the wiring connections, and it provides the programming files of how it works. So it's really great. And so here's an example right here. This is a safety function light curtain using your light curtain, and shows you using not necessarily light curtain controller, but just a light curtain in your guard logics controller. Well, so this is a different style of guard logics, but a guard logics controller, whether it's an L7 or L8 or an L43 like this, it's still going to be applicable. It shows you remote Ethernet safety I/O. It shows dual contactors, e-stop reset. So so here's what your safety rating is right here. It goes and it goes through and breaks it all down. This is a manual, and this is a manual that we're going to be using. And so on the lab, all I did was say, hey, go and look at the application manual for this setup for part A. Then part B, go look at the application manual for this one, then this one. And basically, you just go right through the application manual, and you wire it up exactly as shown. You program it exactly as shown. You configure it exactly as shown, and boom, you're in business. And so it's really cool here. So when we do our capstone, and we want to incorporate some of this stuff, you just got to go find the application manual and then wire it up and program it exactly as shown. So that is going to be what the lab is going to be going through some of these. All right. As we work through this, you know, the safety instruction set has changed a little bit here. And so, you know, some of this stuff still exists, but so if you're familiar with, you know, the way something was looking before, it's still there, but you know, the DCS is an instruction that we can use, and this one is pretty flexible. You can use this for e-stops, light curtains, dual contact, dual safety for a standard motor controller or a power flex, or you know, things like this. So just be aware that these are going to be look at a little bit different, and what is called for in the application example might be different than what you're used to, but it's pretty cool. Okay, so that was once again a kind of a quick one. We'll have a little light curtain trainer board that you might have to build up depending on where we're at and how you're coming through. You might have to do a little work on the remote Ethernet IP boards too, because we're adding that safety I/O block, input and output block. Servo quiz coming soon. We'll talk about it, and then you have the lab to do. So that's what I got for you this week.